Greetings to all the participants present here. On behalf of QA Research and Publications, I would like to welcome you all for the webinar on Predicting the Future Introduction to Regression Analysis. To start with, let me give you a brief about QA Research and Publications. QA serves as a platform to publish research articles in prominent journals and conferences proceedings. We assist authors in publishing their research findings in high impact factor journals, promoting their work, enhancing their reputation, and building a strong scientific profile. Among several indexing databases, Scopus is one of the most preferred for publishing articles. The wide recognition and impact of these journals makes them highly valued in their academic career. We have recently collaborated with Scopus Q1 journal, F1000 Research, published by Taylor and Francis. The authors can now easily submit their articles through a partnered gateway with FN1000. FN1000 Research is an open research publishing platform for scientists, scholars, and clinicians that offers rapid publication of articles and other research outputs without editorial bias. All articles benefits from transparent peer review and editorial guidance on making all source data openly available. Now, I would like to welcome our speaker, Ms. Nurul Jana Noor Hazmi, who is a biostatistics lecturer at Mahasa University, Faculty of Dentistry, holds an MS in medical statistics from the University Science Malaysia. She commenced her career at the Center of Excellence for Research in AIDS at University of Malaya, serving as data manager, medical statistician for 4 years. Trained at Singapore General Hospital, she introduced the Research Electronic Data Capture REDCap system at the University of Malaya in 2015. This initiative has had a significant impact with REDCap now implemented in 12 Malaysian institutions, including the Ministry of Health, showcasing her influence in advanced research methodologies and data management. Beyond the research, she actively educates undergraduate and postgraduate students specializing in research methodology and biostatistics. Our involvement extends to various webinars and workshops demonstrating a dedication to disseminating knowledge beyond traditional classrooms. Once again, I would like to welcome you, Doctor. You may start now.
Hi, Assalamualaikum, and a very good afternoon. Can you see me?
Yes.
All right. Okay. Assalamualaikum, and a very good afternoon. Thank you very much for the introduction just now. My name is Jannah. I'm a lecturer in biostatistics from Faculty of Dentistry, Masa University, located in Kuala Lumpur, Malaysia. Um, I currently okay for now we are going to do a webinar on introduction to regression analysis. So since this webinar is only for 1 hour, I can only cover the basic theory about the regression analysis, and then after that we can go further details into simple linear regression. If we have more time, we can do multiple linear regression. All right. So usually when I did my lecture or webinar, I always ask my participant to do hands-on together with me. So I hope all of you already have SPSS installed in your laptop, and then I already sent the data set. I hope all of you already have it, because I believe if you don't do the hands-on together with me, you will not be able to understand it very well. So I'm using SPSS version 27. If you are using version 29, so it will be a slightly it will be slightly different in terms of interface. All right. Can you see my screen?
Yes.
Okay, thank you so much. Okay, what is regression analysis? So this is actually the common thing that people always ask me. Have you ever heard the word about machine learning? So machine learning is actually a branch of artificial intelligence, or we call it AI. So it involves algorithm and also statistical model that help computer to identify data patterns and also making prediction. So regression analysis is actually a part of machine learning. So we apply machine learning in our daily life. For example, we use machine learning to predict changes in the stock market. We use it to predict the climate and also environment. We use it in healthcare system, education system, and then so on. So the concept of regression model was introduced back in the year 1805 by the famous French mathematician called Adrien Marie Legendre. So this is the person. So since then, the concept of a regression model has remained fundamental in applied statistics. So the reason we use regression analysis because we want to estimate the relationship between the dependent variable and also one or more independent variable. Okay, before we go for the detail, I'm going to explain to you the differences between dependent variable and also independent variable. Okay, I always highlight the importance of basic terms in statistics because if you don't understand the basic terms, you will not be able to do the statistical analysis and you will not be able to choose the right statistical test for your research. Okay, dependent variable is actually the outcome of your research. If you talk to someone about your research project, you talk to someone about the outcome of your research, you are actually talking about the dependent variable. Independent variable is actually the predictor variable or the risk factor that affect the outcome of the study or the dependent variable. Okay, I'm going to give you an example, explaining the differences between independent variable and also dependent variable. Independent variable is the variable that is changed, while dependent variable is the variable affected by the change. So in other words, independent variable is the variable that affect the outcome of the study or the dependent variable. Okay, in this scenario, we have the example of the amount of water as the independent variable. And then we have three dependent variables such as size of plant, number of leaf, and also the survival of the plant. So in this case, we want to see whether amount of water affect the size of plant, whether amount of water affect the number of leaf, whether amount of water affect the survival of the plant. Okay, I hope by now you can differentiate between independent variable and also dependent variable. So this is a very important thing for you to understand, because if you don't understand the differentiation between these two variables, you will not be able to choose the right statistical analysis for your research project. So I'm giving you another example. Let's say if you want to determine the relationship between age and also cholesterol level. Okay, so in this case, cholesterol level is the outcome of the study, and then age is the risk factor that is associated with the cholesterol level. So age is the independent variable, and then cholesterol level is the dependent variable, which is the outcome of the study. So when to apply regression analysis? So the reason we use regression analysis, the first reason is because we want to make a prediction. If you want to make a prediction, use regression analysis. And then another reason, such as we want to see a relationship between the dependent and also independent variable, and then you want to see which variable that actually contribute most to the outcome of measurement, and then so on. Okay, for example, in this case, we have blood pressure as the outcome of the research, which is the dependent variable, and we have risk factors such as age and also diet. So here we want to see whether these predictors or factors are actually associated with the blood pressure, whether we want to see whether age and diet are associated with the blood pressure. So blood pressure is the outcome of the research or dependent variable, and then age and diet are the independent variables. Okay, another example is that the dependent variable or the outcome of the study is the length of hospital stay, And then we have predictive variables that consist of age, treatment method, and also severity of illness. So here we want to see whether these predictors, age, treatment methods, and also severity of illness are associated with the length of hospital stay. So the length of hospital stay is the outcome, and then these three factors are the independent variable. All right. Okay, so in regression analysis, we always have to come up with we call it regression model or regression equation. So this is the basic regression model that consists of single predictor, one outcome variable, and also one coefficient. So this is the basic regression model. We have y equal to b naught plus b1 s1 plus error, where y is the outcome, which is the dependent variable. Okay, this is the reason why you have to know the differences between dependent and also independent variable. B naught here is the intercept of the regression line, and then B1 is the slope of the line, or we call it regression coefficient for independent variable. And then S1 here is the independent variable, and then error is actually residual. So I'm going to explain the detail later on about about the regression model. Okay, so this is the scatter plot. Looking at the relationship between length of baby and also maternal height. So this is the y-axis. This is the x-axis. So y-axis is the length. Y-axis is the length of baby, or it is actually the dependent variable. Maternal height is its x-axis, which is actually the independent variable. So here we want to make the prediction of the length of baby based on maternal height. So this line here, we call it regression line. Okay, let's say if you want to make a prediction of maternal height, let's say the maternal height is 155 cm. So the length of baby should be 50 cm. Okay, another example, if you want to make a prediction of 175 cm of maternal height, so the length of baby should be 54 cm. So now, this I'm going to explain about the error. Error is actually coming from this equation. Okay, error equal to residual. So all the dots here is actually the observation or the actual value. So the line here is the prediction line, which is the predicted value. So the error or residual is actually the difference between the actual value of the observed value and also the predicted value. Okay, this is the meaning of the error or the residual. So I repeat once again, error, or we call it as residual, is the differences between actual value and also predicted value. Okay. Okay, now we're going to go further details into simple linear regression. Simple linear regression is used if you want to estimate the relationship between two quantitative variables. Your dependent variable is quantitative or numerical, and then your independent variable is also numerical. So people always confuse simple linear regression and also Pearson correlation. Okay, so the difference between these two is that is that in simple linear regression, you are interested in making prediction. But Pearson correlation, you're not interested in prediction. You are only interested to see the relationship between dependent and also independent. And then at the same time, you want to see the strength of the relationship. But if you're interested with prediction, you can automatically use simple linear regression, but you have to make sure your dependent variable is numerical, and then your independent variable is also numerical. So when to apply simple linear regression? So the reason we want to use simple linear regression is that we want to predict. We want to predict the value of one variable for a given value of the other. So remember the regression equation I mentioned just now. Okay, this is the regression. This is the regression model. So y equal to b naught plus b1 s1. So now we are going to make the estimation of the outcome based on the independent variable. So this is what we are going to achieve in simple linear regression or in regression analysis. Okay, so I'm going to explain to you the differences between simple linear regression and also multiple linear regression. So in simple linear regression, we're only interested with one independent variable. So the dependent variable is should be numerical variable, and then independent variable should be numerical variable as well. For example, in this case, we have length of baby as a dependent variable, and the mother's height as the independent variable. So you have to make sure both independent and dependent numerical. Okay, in multiple linear regression, it is actually the extension from simple linear regression. In simple linear, you only have one independent variable. In multiple linear, you have more than one independent variables, but the outcome or dependent variable should be numerical variable. So in this case, the dependent variable is the length of baby, and then independent variable consists of mother's height, mother's weight, and also age. So all variables in the independent variable must be numerical variable as well. Okay, but what happens if your independent variables are actually combination between numerical and also categorical, or you only have categorical variables only? Because every research project is different, right? And sometimes you want to add a categorical variable, sometimes you only have a numerical variables. Okay, so it depends on the research project. So let's say if your independent variable is a combination of numerical and also categorical, or you only have categorical variable, but your dependent is numerical variable, you want to use multiple linear regression. So this kind of regression analysis called general linear regression. So the steps of general linear regression is actually almost similar with multiple linear regression, because the differences is that in general linear regression is also consists of categorical variable. Okay, this is the regression equation. This is actually similar with y equal to b naught plus b1 s1 that I mentioned just now. So y equal to a plus bx. So actually you already have learned this when you were in school back then. So this I'm going to show you the theory behind y equal to a plus bx, or y equal to b naught plus b1 s1. So it's basically the same thing. So y is actually the dependent variable. So this is the y-axis. This is a dependent variable. And then x here is the independent variable. A, this is the value of A, which is the intercept. Okay, the intercept of the regression line. And then B here is the slope of the line, which is the value of the regression coefficient for the independent variable. So when I show you the example later on, I'm pretty sure you will understand. All right. So y equal to a plus bx. So it's actually similar with y equal to b naught plus b1 s1. So in regression analysis, we are also interested with coefficient of determination, or we call it R square. Okay, so this value is actually a range from 0 to 1. It's always positive because it's R square. So this is actually provide a measure of how well future outcomes are likely to be predicted by the model. Or in other words, is how much the independent variable, which is x, is explained by the dependent variable, which is y. So later on, when I show you the example, how we interpret the coefficient of determination by looking at the SPSS output, I'm pretty sure you will understand better. So in simple linear regression, we have 4 assumptions that needs to be checked. We have a linearity assumption, we have independent assumption, normality distributed, and also equivariances. So you can use this keyword line. So for L, so you have to make sure the relationship between the independent and also dependent variable is linear or linearity. And the second one, independent observation. So independent observation doesn't have to be checked during the data analysis. So you just have to make sure the observation is independent when you do the data collection previously. And then for the normally distributed, you have to make sure the residual should be approximately normally distributed. So the residual coming from the error just now, from the formula, the differences between the observed value and also predicted value. And the last one, you have to check for the homoscedasticity, or we call it equivariances. So homoscedasticity or equivariances actually to make sure the variability or the spread of the residual is consistent across the independent variable. Okay, so we are going to check for each of the assumption we have. So we have 4 assumptions altogether. So the first one is linearity assumption. So we want to make sure there is linear relationship between the independent and also dependent variable. So how to check the assumption? You have to plot a scatter plot between independent and also dependent variable. And then the second one, for independent observation, you don't have to check during the data analysis. So you just have to make sure your observations are independent. So it can be done during the design stage. And the third one, the residual, which is the coming from the differences between observed and also predicted, should be approximately normally distributed. So how to check for this normality? You have to plot a histogram of residual and then look at the bell-shaped curve. If there is a bell-shaped curve, so it means that the residual is normally distributed. If there is no bell-shaped curve, it means that the residual is not normally distributed. Okay, the last one for homoscedasticity or equivariances. So you have to plot a scatter plot between residual and also predicted values. So you actually can use this keyword SPYR. So x-axis put predicted, y-axis put residual. So later on, I'm going to show you one by one how we are going to check assumption for each how we're going to check for each of the assumption. Okay, now please open dataset birth week. I hope all of you already have dataset with you. So we are going to do hands-on how to conduct a simple linear regression. So I'm using a species version 27. If you are using version 29, it will be slightly different. And then if you have encountered any problem during the hands-on, you just let me know. Maybe we can try to fix the problem together. All right? I hope you can see my data set as well.
Yes, doctor.
Stop. Okay, this dataset contains information on newborn babies and also their parents. So in this case, we want to see whether there is any relationship between maternal height and also the length of baby. Okay, a study was conducted to determine the relationship between mother's height and also the length of baby, with the researcher aiming to forecast the baby's length by using the mother's height as a predictor. So the first thing that you want to do when you want to choose the right statistical analysis is you look at your research objective, list down all the variables that you have, refer to your dataset, identify the type of variable that you have, whether it is numerical and also categorical. And the last one, you can identify the right statistical analysis. So in this case, we have 2 variables that we are going to use. We have the length of baby. We also have mother's height. So these this variable can be referred to the data set. So in this data set, we have mother's height, which is M height, and also length. So the length here is actually the baby's length. So first you have to list down all the variables that you have. So we have mother's height and also the length of baby. After that, we have to identify the types of variable. So these two variables are numerical variable. Okay, these two variables are numerical variables. So you can refer to your data set whether it is numerical or categorical. After that, you can identify the right statistical analysis. Since your dependent variable and also independent variable are numerical variable, so you can choose either Pearson correlation or simple linear regression. But in this case, the researcher is actually aiming to forecast or make prediction. So when we talk about prediction, you're actually talking about regression analysis. You will just want to see the relationship between these two variables without without taking into consideration about the forecast or prediction, then you can use Pearson correlation. But in this case, we want to make a prediction, then we can use simple linear regression. Okay, I'm going to ask you a question. So mother's height and also the length of baby, which one is actually dependent variable? Which one is dependent variable? Which one is independent variable? Okay, which variable do you think is outcome or dependent variable? Anyone want to answer the question? Okay, so in this case, the dependent variable or the outcome of the study is the length of baby. And then the predictor or the independent variable is the mother's height. Okay? Okay, correct. Mother's height is the independent and the length of baby is the dependent variable. So since we are going to make a prediction, so the right statistical analysis is simple linear regression. So the null hypothesis is there is no relationship between mother's height and also the length of baby. And an alternative hypothesis, which is the inverse of null hypothesis, is there is a relationship between mother's height and also the length of baby. Okay, now we are going to run simple linear regression. So you can do it together with me. If you have any question during the hands-on session, just let me know, all right? So now we are going to run simple linear regression. So I hope you can see my screen, both dataset and also the lecture material at the same time. So now go to analyze, okay? And then go to regression. And then go to linear, okay? Analyze, regression, and linear. So which one is dependent variable? So you have to put in dependent variable and also independent variable. So in this case, the dependent variable is the length of baby. So enter length of baby into dependent variable, and then maternal height or mother's height into independent variable. So after that, go to statistics. Okay, go to statistics and then click confidence interval. And then click continue. And then OK. So see, we have another window appear, which is the output of the SPSS. So in this output, we have 4 tables. So look at the last table. So this is the table, the coefficient table. This is a table that we are more interested in. So look at the value for this one. The value for B is the regression coefficient. So remember, y equal to B naught plus B1 x1. So B naught is actually the intercept, which is the value for the constant 15.33. While the value for the maternal height, which is 0.22, is the value for the B1, the regression coefficient for the independent variable. So look at the p-value. So you look at the p-value for the maternal height or independent variable. So we usually use cutoff point 0.05. Okay, we use cutoff point 0.05. If the p-value is less than 0.05, so it means that the result is statistically significant. So in this case, the result is statistically significant. So we can say that maternal height has effect on length of baby. Okay, so look at the second table, which is the model summary. So remember the coefficient of determination, R square. So R square can be taken from model summary. So you can change this value into percentage, which is 23.5%. So you can do the interpretation like this. 23.5% of the variation in the length of baby is explained by mother's height. So it means that the balance 76.5% is explained by other factors, but 23.5% of the variation is explained by mother's height. Okay, the next one is the ANOVA table. So you look at the ANOVA table. So you look at the last column. This is the p-value. If the p-value here is less than 0.05, so it means that the regression model can predict the dependent variable significantly well. So the function of ANOVA table is that we want to test the overall significance of the regression model. So in this case, we can say that the regression model can predict the dependent variable significantly well because the p-value here is less than 0.05. If the p-value is more than 0.05, so it means that the regression model cannot predict the dependent variable significantly well. Okay, the next one. So once you have come up with the simple linear regression, then you can prepare the table for the simple linear regression like this. I always mention this to my participant and also my student. Do not copy the table that you get from SPSS output and put in your research report and manuscript or so on. Otherwise, you have to prepare your own table nicely because we don't need all the information that we get from SPSS. We just need certain information. So in this case, for simple linear regression, you can add a regression coefficient. So the value of B is the regression coefficient coming from this table, coefficient table. And then we have the p-value 0.001. And also we can also include the 95% confidence interval. Okay, I hope you can understand how to do simple linear regression. So later I'm going to explain how to check the assumption for each how to check the assumption, and then after that we can come up with the regression equation. But please keep in mind that in order for you to come up with the regression equation or regression model, you have to make sure the p-value during the simple linear regression is significant. If the p-value is not significant, then you cannot come out with the regression model. Okay, you can only do the prediction if the p-value is significant. Okay, now we are going to check assumption for every assumptions that we have. So the first one, independent observation, you don't have to check. The second one, you have to make sure the relationship between independent and also dependent variable is linear, or we call it linearity. So here we are going to build a scatter plot between independent and also dependent variable. And the third one is about homoscedasticity or equal variances. And then for this one, we are going to plot a scatter plot between residual and also predicted values. So you can use this keyword SPYR, which is x-axis is predicted, y-axis is residual. And then the fourth, residual should be approximately normally distributed. So you can check by using a histogram. You have to plot the histogram of residual. Look at whether there is a bell-shaped curve or not. If there is a bell-shaped curve, it means that the residual is normally distributed. If it doesn't have bell-shaped curve, it means that the residual is not normally distributed. Okay, so now we're going to check the assumption one by one. So the first one, let's check a linearity assumption. So remember, for linearity, we are going to plot a scatter plot between independent and also dependent variable. Okay, to do this, you can go to graph. You can go to graph, legacy dialogues, and then go to you can go to scatter or dot. And then after that, click define. So here we have y-axis and then x-axis. So y-axis is actually your dependent variable. X-axis is independent variable. So in this case, length of baby is the dependent variable. So enter length of baby into y-axis and then enter maternal height into x-axis. Okay. After that, you can click OK. Okay, click OK. And now you can see we have the scatter plot between length of baby and also maternal height. Now we want to see whether there is linear relationship between these two. So what you can do is, you can double click this scatter plot and then click add fit line at total. So you can see there is linear relationship between length of baby and also maternal height. Okay, so you look at this node. So this is an example of linear and also non-linear relationship. So it means that positive linearity. So this one negative linearity. So this is example of non-linear relationship. So what you have to do is you can just plot independent and also dependent variable and then do this. We call it regression line. Okay, the second one is homoscedasticity or equivariances. So homoscedasticity or equivariances is actually we want to see the variability or spread of the residual across the independent variable. So we want to make sure the dispersion of the residual is consistent. Okay, so now we are going to do homoscedasticity. So now go to analyze, regression, and also linear. Analyze, regression, linear. Okay. So remember, for homoscedasticity, the keyword is we are going to plot the scatter plot between residual and also predicted value. So first, you have to come up with the residual values and also predicted value. So to do this, what you're going to do is you have to click statistics, save. Go to save. And then under predicted values, click unstandardized. Under residual, click unstandardized. And then click continue. And then OK. So now look at your data set. Look at last column. So now we are actually created two additional variables for predicted and also residual. So how SPSS come up with predicted and also residual? So this is actually coming from the regression coefficient. Okay, so this is the regression coefficient or regression equation or model. So y equal to a plus bx. So y is the dependent variable, which is length of baby. So a is the intercept value, which is the value regression coefficient for the constant, which is 15.33. And then B is actually the value for the regression coefficient for the independent variable, which is 0.22. And then the independent variable, which is mother's height. So to make a prediction, you just put in any values for the mother's height, and then you can come up with the length of baby. Okay, for example, in this case, so look at this example. This one is coming from SPSS. Okay, so the length of baby. So here, the mother's height is 162. So you put in 162 into this equation. So 15.33 plus 0.22 times 162, and then you get 50.97, which is the value for the predicted. But please keep in mind that there will be a slightly different when you from the calculation from the SPSS, and also when you calculate it manually. So this value is actually taken from this equation when you put in the mother's height. Okay, how about the residual? So remember, the formula for the residual is the differences between observed value and also predicted value. Okay, observed minus predicted value, or the length of baby. So residual is actually 56, the length of baby is the observed minus predicted 50.8. And then after that, you get 5.2. So 5.2 is actually the value for the residual. So you have to remember this formula. So residual is a difference between observed and also predicted length or predicted value. So the length is actually the length of baby lah. So observed minus predicted. So this is how we get how SPSS calculated the predicted value and also residual value. Okay, now we are going to put the scatter plot between XP, YR. Okay, so to plot this, go to Analyze, go to Graph, Legacy Dialogs, and then go to Scatter or Dot, and then click Define. So remember, for this SPYR, okay, remove these two variables from y-axis and also x-axis. So SPYR, okay, P predicted should be in x-axis, residual should be in y-axis. So SPYR, okay, and then click OK. Sorry, you cannot see my screen. Can you see my lecture note and also the data set together? Only seeing the SPSS output. Okay, so you cannot see the lecture note? Oh, I
Yes,
see.
doctor.
I see. What about you, Gulmira? You can see both my lecture note and also SPSS together? Oh, I see. Oh, all right. I tried to do the sharing once again. I see. Oh, okay. So now, can you see both my lecture note and also SPSS? Okay, good. I think I already checked almost all the assumptions. So you want me to repeat again some of it, or I can just continue? You want me to repeat anything? Okay. Okay, so I'll just Okay, go over on the assumption. So I'll start again on the assumption. Okay. So I will start again for the assumption. All right. So the first assumption that we are going to check is linearity. Okay. So linearity can be checked by plotting the scatter plot between independent and also dependent variable. Okay. To do this, what you can do is you go to analyze, you go to graph, legacy dialogues, and also scatter or dot, and then click define. So here we have y-axis and also x-axis. So y-axis is the dependent variable, which is the length of baby. So enter the length of baby into y-axis, and then enter maternal height into x-axis. And then after that, you can just click OK. Okay. So once you click OK, so now we are checking for linearity. So we want to see whether there is linear relationship between length of baby and also maternal height. So double click scatter plot and then click add fit line at total. So you can see there is linear relationship between length of baby and also maternal height. So this is actually positive relationship. Okay, so it means that the linearity assumption is met for the linearity. Okay, the second assumption is homoscedasticity or equal variances. So for homoscedasticity, we want to make sure the residual, okay, we want to make sure the residual is consistent, okay, is consistent or is consistent. So to do this, you can do by plotting the scatter plot between residual and also predicted values by using this keyword SPYR. So x-axis predicted, y-axis residual. Okay. So to do this, first you are going to come up with the value for the predicted and also residual value. So go to analyze, regression, and also linear. And then you can go to save. And then you can click unstandardized for predicted values and also unstandardized for residual value. After that, you can just click continue. And then you can see in your dataset, we have a new additional variable that has predicted value and also residual values. So how we come up with predicted and residual values coming from the regression equation y equal to a plus y equal to a plus bx. So y equal to a plus bx. So y is the outcome, which is the length of baby, and then a is the intercept, which is the regression coefficient for the constant, which is 15.33. And then we put in the value for the regression coefficient for the independent variable, which is 0.22 times mother's height, which is the independent variable. So this is the regression equation that we can come up with. But please remember, this equation can only be written if the p-value for the independent variable is significant. If the p-value is not significant, you cannot come up with a regression equation. Okay, so how to come up with the predicted? So you put in all the value in the mother's height. For example, I want to put in 162 in the regression equation. So 15.33 plus 0.22 times 162, and then we get 50.97 or 15.79650. So this is how we get the value for the predicted. And then for the residual, so the formula for the residual is the observed value minus predicted value. So the length is actually the length of baby. So in this case, 56, which is the length of baby, minus 50.8 taken from the predicted value. And then we get 5.2. So this is how as best as calculated, predicted, and also residual. Okay. So now we are going to check for the the homoscedasticity by plotting SPYR. So to do that, go to graph, legacy dialogues, and then go to scatter or dot, and then click define. And then remove both length of baby and also maternal height. So remember SPYR. So predicted, go to x-axis, and residual go to y-axis. So remember x, p, y, r, and then click OK. So once you click OK, we can see there is a scatter plot between residual and also predicted value. So double click this scatter plot and then click this one, add a reference line to the y-axis. Okay, so click this one. Okay, so you look at what's the difference between homoscedasticity or heteroscedasticity or unequal variances. If your scatter plot, if the pattern of your scatter plot is like this, okay, it's like this. So we call it unequal variances or heteroscedasticity. If the dot is scattered all over the place or like this or something like this, we call it homoscedasticity or equal variances is met. So for this case, the assumption for the homoscedasticity is met. Okay, the next one, we are going to check for the assumption for the residual, for the normality distribution for the residual. So now go to graph, legacy dialogues, and then go to histogram. We are going to plot the histogram of residual, okay? And then put residual in the variable, and then click display normal curve, okay? Put residual and then click display normal curve, and then click OK. And then you can see this is we call it bell-shaped curve. Okay, we call it bell-shaped curve. So it means that the residual is normally distributed. If you don't have bell-shaped, if the scatter plot doesn't, if the histogram doesn't have bell-shaped curve, so it means that the residual is not normally distributed. Okay, so based on this assumption, we can say that all assumptions are met. Assumption for homoscedasticity, assumption for linearity, and then assumption for normality distribution are all met. But what happens if one of the assumption or more than one of the assumption are not met? So usually if the assumption are not met, what you can do is first you can consider to do data transformation by using logarithm, or you can also use the square root of your data, or you can also consider to use non-parametric approach for regression analysis called kernel regression. Another things that you can do is that you can also consider to grouping your data, okay, into categorical variables. So we have ways of dealing with violation of assumption. Okay, so next one. So once you have checked all the assumptions, so it means that you already have the model, you already have the regression model for the simple linear regression. So this is the result for the regression for the simple linear regression. So you can come up with a regression equation based on this table. Okay, so y equal to a plus bx, or y equal to b naught plus b1 s1. So length of baby equal to 15.33 plus 0.22 times mother's height. So this is how we do the interpretation. Increasing the mother's height by 1 cm will result in a 0.2 cm increase in the length of the baby. And then after that, you can add the value for the regression coefficient, which is 0.22, together with the 95% confidence interval 0.09 and also 0.35, and the p-value 0.001. But please keep in mind that this regression equation can be written like this, and interpretation can be written like this once the p-value is significant. If the p-value is not significant, you cannot come up with the regression equation. All right? So I hope by now you can understand about simple linear regression. Okay, so what time is it? Okay, so for the So I'm going to explain to you the differentiation between each of the regression analysis. So actually we have many type of regression analysis, but I'm going to show you example. I'm going to explain to you the differentiation for this regression analysis. So the first column we have here is the dependent variable, and then we have independent variable and the statistical analysis. So the first row, dependent variable is numerical variable. And then independent variable is numerical. If you only have one numerical independent variable, you can use simple linear regression. If you have more than one independent variable, okay, then you can use multiple linear regression. But if the independent variable is a combination between numerical and also categorical variable, or you only have categorical variables only, then the right statistical analysis is general linear regression. So the step for the general linear regression and also multiple linear regression is actually almost similar. Okay, the second one, the dependent variable is the categorical variable, and then it is dichotomous. Dichotomous means that you have only two levels. The variable is categorical, but you only have two levels. For example, yes, no, true, false, and then so on. And an independent variable, okay, it can be the combination between numerical and also categorical variable. Okay, in this case, you can use multiple or binary logistic regression. Okay, the third one, the dependent variable is categorical variable, same goes as second one. But in this case, the variable is polytomous. You have more than two levels, and it is also nominal, which is unordered category. For example, type of diseases. Okay, type of diseases, let's say you have more than two diseases, okay, under the category of type of diseases. And then this type of diseases is nominal, is unordered category. Okay. And then independent variable, it can be the combination between numerical and also categorical variable. So the right statistical analysis is multinomial logistic regression. So the last one, the dependent variable is the categorical variable. So almost similar with the third one, but here you have more than two levels, but it is ordinal. For example, disease severity, we have mild, moderate, severe. Okay, the mild, moderate, severe is order category. So we always start with mild, followed by moderate, and also severe. And then the independent variable can be the combination between numerical and also categorical variable. So since the outcome here is the categorical and it is ordinal, so we can use ordinal logistic regression. So from my experience, I haven't used SPSS to run multinomial and also ordinal logistic regression. I always use Stata to run the analysis. So I'm not sure whether SPSS can be used to run multinomial and also ordinal logistic regression. So since I think we have a few minutes, okay, we have a few minutes, maybe I can show you a little bit the overview about multiple linear regression. Okay, multiple linear regression is used if you want to estimate the relationship between two or more independent variable, and then you have numerical dependent variable. So dependent variable must be numerical. Independent variable should be two or more numerical variables. So multiple linear regression is the extension from simple linear regression. So in simple linear regression, you only have one independent variable, but in multiple linear regression, you have more than one independent variables, and then all variables are numerical variables. Okay, but what happens if you have if you have a combination of numerical and categorical or categorical only, you can use general linear regression. Okay, these are differences between simple linear regression and also multiple linear regression. I hope by now you can understand the differentiation between these two. Okay, this is the multiple linear regression model. So as you can see just now in simple linear regression, we end until B1 S1, y equal to B0 plus B1 S1. Because in simple linear regression, we only have one independent variable. But in multiple linear regression, we have more than one independent variable. So it depends on your analysis. If you have, let's say, if you have three independent variable, so your regression model should stop at B3 S3. So Y is the outcome, which is the dependent variable. B0 is the intercept. So the value for B1 until Bn is actually the regression coefficient for each of the independent variable. And then X is the independent variable. Okay, this is the step that you can follow in multiple linear regression analysis. So you can start with descriptive statistics. So the reason we start with descriptive statistics is because we want to do data exploration. We want to see whether there are any missing data or whether there are any outliers. So basically, we want to do data cleaning at this stage. And then after that, you can do simple linear regression. Okay, and then you can come up with the multiple linear regression, and then you can check for multi-covariety and then interaction, and then you can do then you can check for model assumption, and then the last one, you can do interpretation and also result presentation. Okay, so in this case, so our research question is, we want to know what are the factors that are associated with the length of baby. So first, like I explained just now, first we have to list down all the variables that you have in your research objective. So in this case, we have length of baby as the dependent variable. We have factors. When we talk about factors, we are actually talking about more than one factor, more than one independent variable. So factors can be taken from your dataset. So prior to the analysis, we have to identify the list of independent variables that should be added, that you think might be associated with the length of baby. In this case, I think mother's age, height, and also weight might be associated with the length of baby. So I want to test this variable in my analysis. So after that, you can identify the type of variable, whether they are numerical or categorical, and then you can identify the right statistical analysis. So in this case, since the outcome of the study is the length of baby, which is the numerical variable, and then you want to see the factors that are associated with the length of baby, so the right statistical analysis is multiple linear regression. So first, you do descriptive statistics. So look at run categorical data, run numerical data, see the overview of your data, look at the percentage, look at the mean, see whether there are any missing data or outliers. If any errors in the data, do the data cleaning and then fix the problem in your data before you proceed with the second step, which is simple linear regression. So in simple linear regression, since we already identified three independent variables that consist of age, height, and also weight, right? So in this case, you have to analyze simple linear regression for each of the independent variable, and then you identify which variable that has p-value that there is less than 0.0, that has 0.25, and also clinically important. So at this stage, you have to choose the p-value that has less than 0.25, or you think it is clinically important. Okay, you do simple linear regression for each of the variable, and then you identify look at the p-value, identify the right variable to be added to the next step. And in this case, we found that all variables are found to be statistically significant, less than 0.25. Okay, so after that, you can start by using doing multiple linear regression by using the following methods: forward, backward, and also stepwise. Perform all the method and then select all the model with all variables significant, or we call it more parsimonious model. And then after that, you can check for multi-covariety and also interaction term. So multi-covariety and also interaction term can be checked if you have more than one significant independent variable during step number 3. After that, you can check the model assumption that consists of overall linearity, homozygosity, linearity of each independent variable, and then residual should be approximately normally distributed. So almost similar with simple linear regression, but at this stage, we add one more assumption, which is overall linearity, which is SPYR as well. Okay, so once you check all the assumption, you can come up with your final model. So this is your final model. So in this case, we have age and also height found to be significant, and then we can prepare a table for the simple linear regression and also multiple linear regression, and you can see that mother's weight is no longer significant during the multiple linear regression. So at this stage, you can come up with the final model equation that consists of length of baby equal to 35.96, and then include the regression equation and also the independent variable. So this is how we write the multiple linear regression model. So this is only the overview. I cannot cover this during 1 hour of webinar, but I just want to show you the differences between a simple linear regression and also multiple linear regression. So I hope you have an idea. I hope by now you can understand at least simple linear regression, how to do simple linear regression. So I think that's all from me. Do you have any question?
Now the session is open for Q&A. Is there any questions from the participant side? You may ask now.
Actually, many of them direct message me. What if one factor is significant and others are not significant in multiple linear regression? So it means that you only have to include one. You only have to include one factor. No need to include. No need to include the rest of the factors that are not significant. So it means that you only have to come up with simple linear regression, but you still have to check for model assumption. So what to do if P is more than 0.25? If you think the variable is very important, it is clinically important for your research, okay, you can include it. But for me, when I run regression analysis, I always try and error. I try to add this variable and then see how the models come out. And after that, I try to remove the variable. So you cannot just do it once and then you can do the conclusion. You cannot do like this. You have to do many times, try and error. Okay, if we transfer categorical to numerical, can we do simple? If we transfer categorical sex to numerical, how to transfer gender to numerical? Any variable that you can think can transfer to numerical variable, yes, you can do simple linear regression. Oh, it's still considered as categorical variable for the gender, male and female. Okay, so if the assumptions are violated, if one of the assumptions are violated or more than one assumption are violated, you can consider maybe you can do data transformation of your dependent variable. You can use logarithm, or you can use a square of your data. Okay, and then you can also try another approach for non-parametric of regression analysis called kernel regression. But honestly, I haven't done any of this, because when I found my model is not met, I try to adjust the variable. Maybe instead of taking the numerical variable, maybe I change the numerical variable into categories so that I can get so that I can get the right model for my research. So actually, you cannot depend on one try when you do the analysis. You have to do many times so that you can get what you want. Okay, so that's my advice for you. Don't rely on one time, but do it many times until you get what you want. You know, when you're dealing with a real data set, it's totally different compared to hands-on, right? So you can have a lot of maybe difficulties, but you have to try more than once. What if the variable is not normally um what if the variable is not normally distributed? Can we transform the data to normal distribution and then use simple linear regression? Oh, for simple linear regression, you mean for simple linear regression, you mean for residual or the numerical data? So if the numerical data is not normally distributed, you can still use simple linear regression. So it's different with Pearson correlation. For Pearson correlation, if the data is not normally distributed, you have to use Spearman correlation. But simple linear regression is fine to proceed with, to proceed if the data is not normally distributed. Yeah. Okay, can we have the slide for the multiple regression as well? Okay. All right. So I think that's all for today. All right. I know research doing data analysis for the regression analysis is not easy as it sounds, but you have to try many times until you get what you want. All right. So I wish all of you all the best in your research project. Okay. So I think that's all from me. Thank you so much.
Thank you, Doctor. That was a thought provoking talk. Thank you for imparting your knowledge and remarks on the concept. Thank you once again, Doctor. Uh, Participants will receive your certificates and presentation document within 7 to 10 working days. Participants shall register for the webinar through our website.